Ankita, hello. Yes. In yesterday's lecture, what we have covered? कोणी सांगू शकाल मला काय आपण कव्हर केलंय कालच्या लेक्चर मध्ये?
Yes, ma'am.
हा बोला.
आपण लास्ट पॉइंट ASK और बायनरी ASK च एक्सप्लेनेशन होतं, ऍप्लिकेशन पर्यंत झालं.
आणि त्याच्या आधी काय बघितलं आपण?
त्याच्या आधी आपण प्रोबॅबिलिटी ऑफ एरर आणि त्याच्या आधी ते डेरिवेशन जे आपण मागच्या आधीच्या लेक्चरला सुरू केलेलं ते डेरिवेशन त्याचे
Okay.
फ्रिक्वेन्सी ऑफ
ऑप्टिमम थ्रेशोल्डिंग व्हॅल्यू कशी ऑब्टेन करायची ग्राफिकली आणि विथ इक्वेशन.
हा.
Okay. So now I'm going to start with the next content for ASK. But before starting with the next content of ASK, once again I will remind you that this ASK output basic equation is given by a by 2 1 plus mt cos of omega ct, where this mt value will be either plus 1 or minus 1, and that will depend upon what is your bk value. If bk value is 1, mt will become plus 1, and because of that the presence of signal will be at that moment in the modulated output. But if the bk value is 0, then mt will become as minus 1, and because of that there will be absence of signal in the ASK modulated output. And this is how either on or off of the signal will be present, and we will find out there on off keying to be happened. And such type of signal we are finding in radio telegraphy. That was the application for binary ASK signal. So up till this, in yesterday's lecture we have covered out. Now I'm going for the derivation part in form of general expression for the given ASK modulation scheme. आता हे बघताना आपण कुठून सुरुवात करणार आहे? तर झेड म्हणजे काय आहे? आपला ट्रान्समिटेड सिग्नल आहे, आणि तो ट्रान्समिटेड सिग्नल आपण केथ ड्युरेशन मध्ये बघणार आहे. म्हणजे बेस्ड अपॉन केथ ड्युरेशन बिट व्हॅल्यू आयदर 0 or 1, हिअर द transmitted signal will be either shifted version of S1T signal or S2T signal. जनरल मॉडेलिंग मध्ये आपण हे बघितलंय ना. Now, by taking the reference of that general modeling, we are going further for deriving the equation of ASK modulation probability of error. So this is our next task, what we are going to accomplish in the lecture. So for that, we are starting with the ZT signal, and we know ZT is actual transmitted signal, and actual transmitted signal is nothing but the shifted version of either S1T or S2T signal based upon what is the value of BK. But in case of ASK, what we have said, either we are having a presence of signal or the absence of signal, and that's why here we are writing S2T is equal to a cos of omega ct and S1T is equal to 0. Now if I am substituting this S2T into ZT, then ZT will be nothing but dt multiplied with a cos of omega ct, and that's why ZT is what? Transmitter output, and this transmitter for the ASK will be seen to be a product modulator block only. Once again I will repeat the statement. For the transmitter block diagram of the ASK modulation, we will have a product modulator block. And for the product modulator block, we will be having two inputs. One is dt and other one is a cos of omega ct. But now we will understand what is this dt and what is the nature of this a cos of omega ct signal. So here In the next statement, we are saying that dt is nothing but a low pass filter pulse waveform which will consist of rectangular pulses, and every pulse is going to exist for TB duration. So as it is a dt, that is a function of time, so definitely it will be a continuous time variable signal. But as it is a pulse waveform, because of that we will have a discrete pulses which are observed into that dt signal. And the discrete pulses, if they are coming, then mathematically to represent that dt signal, instead of integration we will have the summation operation to be used, because it is a discretized nature of the signal. And to present that signal, the instances which are indicated by k will be varying from minus infinity to plus infinity. So mathematically, that pulse waveform, which is consisting of rectangular pulses, is represented by dt, and as it is a sequence of number of pulses, and number of pulses will be discrete in nature. So here we are using summation sign, and this is a continuous time function. So we are saying the k, that is the instances for the pulse occurrence, will start from minus infinity to plus infinity, and it is given by bk multiplied with g of t minus k minus 1 into tb. So in short, I can say that gt is having a shifted version representation in this given equation of dt. And here bk value will be either 0 or 1. That means this bk is nothing but the bit pattern that we have connected to the given modulator block diagram. And this GT signal value is 1 when the t value is in between 0 to TB. Otherwise, this value will be 0 for other time instances. So in short, what we are doing here, we are multiplying this bk which is 0 or 1 with gt which is shifted version with 0 or 1, and this is how we will find out that dt will be occurring as a pulses at the different time instances, because here k is going to change from minus infinity to plus infinity. Now the next thing what we are saying is, that's why we are having this dt which is nothing but d of t minus t. So here this t is nothing but the random delay with the uniform PDF, and for that the considered interval is the bit interval value only. And that's why, as earlier I have said, ZT, which is a modulated output waveform, is seen to be a product modulation output, and it is obtained by multiplying the carrier means a cos of omega ct signal, and that is multiplied with dt signal, and dt is nothing but a rectangular pulses waveform. And that's why here we can see that the bandwidth which is going to be happened for the ASK modulation is dependent on the value of this a square divided by 4 GD f minus fc plus GD of f plus fc, where this GD of f represents the power spectral density value of the DT signal, because DT signal existence is going to give us the presence or absence of ASK modulated output. And that's why here this power spectral density related to the DT signal is very much important. Now we will talk for the value of bandwidth of the ASK signal. And to talk for the bandwidth of the ASK signal, first we have to define with what rate the ASK signal will be generated, and that will be dependent upon what is the bit rate for the binary signaling system to be defined. So this bit rate we are indicating with FB, and FB is nothing but what? Frequency of generation of bits, that is equal to 1 by TB, where this TB indicates the bit period over which every bit is going to exist. And that's why here we have mentioned that TB is equal to 1 bit period. So the bandwidth which is required for the ASK signal is obviously twice to that of this FB, because here we have to follow again the Nyquist criteria for getting the modulation transmissions to be done. And that's why here the bandwidth required will be twice FB minimum. And as it will possess again the Gaussian nature of the output, and that's why here you can observe that this Gaussian natured behavior for the ASK signal representation will be there, but this ASK output will possess maximum amplitude when your frequency is equal to the carrier frequency, and it will reach to the minimum value at the frequencies which are equal to either Fc minus F or Fc plus F, where this F will be nothing but this considered frequency of the given modulation signal. So the above graph represents the frequency spectrum for the ASK signal. And this frequency spectrum consists of the carrier frequency with upper and lower sidebands. And that's why, if you are remembering, I have said that ASK is nothing but double sideband AM modulation itself. And double sideband will be seen by this Fc minus F and Fc plus F component in the frequency spectrum representation, which will represent the two bands which are located at equal distances around the carrier frequency of the signal. And that's why we are saying that ASK is nothing but the type of double sideband AM modulation. Now, the next thing what we are going to see is mentioning the transmission bandwidth in terms of the bitrate value. And that's why here we are mentioning the bandwidth that is equal to 1 plus R into F, where this R is nothing but the filter characteristic factor, and its value is always in between 0 to 1. And that's how this value of bandwidth will become more if this R value is 1, because it will become equal to twice of F. That is what the value of bandwidth we have derived in previous case for the ASK modulation output. That means the maximum bandwidth for ASK signal is equal to twice F, and that bandwidth is achievable only if your filter characteristic is better or filter designing is proper one. That's how here once again we are commenting that with the proper filter parameter designing only, the probability of error in ASK modulation can be minimized. लक्षात येतंय का रे? Hello?
Yes, ma'am.
लक्षात येतंय? Okay. Now, after this, we are defining for the ASK advantages. And in the ASK advantages, mainly we are commenting regarding the system structure. Just in the modulation process, I told you that for the modulator block diagram, only one product modulator block will be existing. And that's why here this ASK modulation is very easy for generation as well as for detection, because a single block implementation we have to do, and for that single block also the input what we are providing is simply a sinusoidal signal of a cos of omega ct and another signal that is dt, which is a continuous strain of pulses. And that's why this generation process is very easy. Similarly, the detection process is also easy. But until now, the detection process we have not seen. In the next part, we are going to see the detection process. But remember that as an advantage of ASK, both generation and detection are very easy. But as an ASK disadvantage, we can say that as like amplitude modulation, it is very sensitive to the noise. And that's why in less number of applications where the data transmission is going to happen, the ASK will be applied. And that's why if you have read out your mobile that pamphlets also, or any another pamphlets regarding the Tata Docomo or that Jio phones, then you might have read out in that the modulation which have been mentioned will be generally FSK, QPSK, QAM, or the type of MQAMs which have been mentioned, but never ASK is mentioned in any type of mobile communication operation. Generally, the PSK, FSK, and higher order QAM operations will be used in the different processes in wireless communication and in broadband communications also. So after this, we are going for the ASK receiver to be seen. But if you are remembering, at the starting when I have started with this unit, I have told you that either we are having the digital carrier modulation to be classified as binary signaling scheme or MRA signaling scheme. And that classification will be based on how many number of signals, out of those signals, which signals I am going to transmit. That means out of 2 signals or out of m number of signals, the shifting values we are going to occur. But one another method we have seen of classification, and that was based upon whether we are having synchronized, that is phase and frequency synchronized carrier present at transmitter and receiver, that is there or it is not there. Based on that, coherent detection and non-coherent detection, these two types we have mentioned. And so here, when we are going for this ASK reception to be seen, from the received signal, that is the VT signal, from that received signal, two types of demodulator implementations will be possible. So here, the first I have mentioned as integrate and dump type of coherent demodulation, where the another one I have mentioned is non-coherent envelope demodulation procedure. So for ASK receiver, these two different types of reception operation or demodulation operation we are going to check. So to have the coherent demodulation to be obtained, the integrate and dump circuitry we have to use. So below is the presentation of that integrate and dump circuitry. So here you can see why we are saying integrate and dump. So you can have this RC combination. For the RC combination, when we are taking the output across the capacitor, it is nothing but the integration of applied input. And that's why we are saying integrate. And the dumping of these values, which are integrated values across the capacitor, that will be going to happen only when these two switches will get closed. Otherwise, the output dumping is not possible as the path is not closed for getting this integrated output to be forwarded. And that's why this circuit has been named as integrate and dump receiver. Now we will check why it is mentioned as coherent demodulation. Because for the coherent demodulation to exist, we have said that at the receiver also we should have a locally generated carrier, and that locally generated carrier at the receiver should have same phase and frequency as that of the transmitted carrier. And that is what we are observing over here, which is seen with the S2T minus S1T signal. Now, one another thing, please remember that in the generalized receiver block diagram of this signaling scheme, I have told you that for any type of receiver, we will have presence of three basic blocks. Out of that, one block is the filter. After the filter, we will have sampler, and the third block will be the thresholding device. So here in the receiver diagram, again you are observing the filter, then this sampler, and then the thresholding device. Now we will start with the modeling of this coherent ASK modulation operation. And to start with the receiver operation, we have to see from the channel. And on the channel, we know we are putting the transmitted signal ZT. On the channel, this ZT will get added with the white Gaussian noise NT, and such added value, which is indicated as VT signal, will be passed to the receiver. Now, this ZT plus NT will be applied to the filter, which will filter out the noise value from the signal, which is of bandpass type of filter. After getting the noise filtration to be done, the signal component what we are going to get, that will be multiplied with this difference signal of S2T minus S1T. Now let's remember that here for the ASK signaling scheme, at the initial stage, we have mentioned that S1T is 0 and S2T is A cos of omega CT. 1 minute, I will show you that. Yes, here. We have mentioned that S2T is A cos of omega CT and S1T is 0. And that's why here, for this derivation of S2T minus S1T, the answer will be A cos of omega CT. So whatever the modulated output is there, that modulated output will get multiplied with A cos of omega CT signal. And we know this modulated output will have either the presence of signal, and if presence of signal is there, that is also A cos of omega CT signal, and at the other bit period there is absence of signal. And if absence of signal is there, then that signal component value is 0. So the signal component at the multiplier which is got filtered will either have magnitude as A cos of omega CT, or it will be 0 because it is ASK modulated output. And this subtraction component will have the value as A cos of omega CT. So the multiplication resultant will be either A square cos square omega CT, or it will be 0 based on what is the modulated output. And that component now will be applied to this integrator, which is a RC network. Now this a square cos square omega ct or 0 output, which is integrated across this capacitor, will be given from this output only if the switches are closed. If these switches are closed, then only that a square cos square omega ct or 0, whatever is existing, that will be given to this thresholding device. And the thresholding device will compare this a square cos square omega ct with thresholding level or 0 with thresholding level, and based on that, from the thresholding device, the 0 or 1 bit will get decoded. This is how in the coherent ASK demodulation 0 1 will get decoded. But please remember that the switch closing, that is sampling, is going to happen after every TB second. That means sampling duration is of TB period. And why this is done? Because we know that in ASK modulations or in any shift keying modulations, the output is going to change after every TB period, and that's why here sampling is also done after every TB duration. This is what I have mentioned in this lower part of explanation. Just I told you that S2T here will be A cos of omega ct, S1T will be 0. So this difference signal will be A cos of omega ct. The receiver output at the end of signaling interval we are representing either with S01 KTB or S02 KTB. So S1T here we have mentioned at 0. So this subtraction resultant multiplied with the output from ASK, that will result into 0, or as I have said earlier, if S2T is present, it is A cos of omega ct, and this subtraction resultant is also A cos of omega ct, and that resultant will comes out as A square cos of omega ct. But A square is constant, so we are taking that outside, and this cos square omega ct that we have integrated with respect to the limits of 0 to TB, and after getting that integration to be carried out, substitute the limits of 0 and TB, finally we will get this answer for the output as A square divided by 2 TB. So this is some mathematical rearrangement that has been done. Then in the preceding step, we have assumed that omega CTB is equal to twice n pi. Now what is the meaning of this omega CTB is equal to twice n pi? Twice n pi will indicate the repetition period, and this repetition period, that is periodicity, is going to happen, or it is dependent upon the carrier frequency and the bit period of the signal. And that's how here we are saying that the repetitiveness in the ASK modulated output will depend upon this value of carrier frequency and the bit period consideration. Then one another thing we have to do here, and that is the optimum threshold value setting for the ASK receiver. And we have derived mathematically that optimum threshold setting will be done by calculating the average value of the S01 T output and S02 output, which are correspondingly the modulator output or received output with respect to S1T and with respect to S2T signal. And here just now we have derived the S01 KTB value, which is equal to 0, and S02 KTB value as A square divided by 2 TB. So let's put those two values over here. So 0 plus A square divided by 2 TB, and initially in the denominator for averaging 2 is there. So because of that, in denominator the 4 will occur. So the value will become as a square divided by 4TB for optimum threshold of ASK coherent receiver. So with respect to this optimum threshold value, either a square cos square omega ct will be compared or 0 will be compared, and based on that the transmitted bit decoding will be done as 0 or 1. Now we will check what is the value of probability of error for this ASK modulation. So this will depend upon sigma square x. So gamma square x. So gamma square max is nothing but the maximum value of transfer function of filter. Because just now, previous to this derivation part, I have told you that based upon the filter function or based upon the filter parameter definition, the probability of error will be dependent. And that will be defined as a ratio of PF square divided by GNF, which is integrated over the period of minus infinity to plus infinity, because filter has to be implemented to remove out the noise signal, and noise is existing from minus infinity to plus infinity. So here this gamma square max has to be carried out for the period of minus infinity to plus infinity. This GNF will indicate the noise power spectral density representation, while PF square will indicate the signal power spectral density. And this probability of error is going to lie with the Gaussian probability density function, and for this Gaussian probability density function, the sigma square, that is variance value, will be equal to 1, because ZT will be always having the output average value which is equal to 1, and that's why here the sigma square in original Gaussian PDF equation will be substituted as 1 in under root position, and also in this denominator position with multiplied with this 2. And that's why the probability of error equation will change as summation from sigma max divided by 2 to plus infinity 1 divided by under root 2 pi, as sigma square is equal to 1 over here, exponential term e raised to here actually x square, but x is your received signal, so it is z square divided by 2. That will be going to happen. And this probability of error is now converted in terms of a Q function. So Q function is a type of PDF representation only, and it is seen as a inverse function representation of Gaussian PDF. So on net you can search for relationship between the Q function and Gaussian PDF, or in any of the digital communication book, in the appendix part you will find the description for the Q function representation. Generally, the Q functions are nothing but the inverse function representation of Gaussian PDF equations. Now, for this gamma square max, how we are finding the output that we are going to derive here with respect to the substituted values from the p square t. P square t is nothing but what? Signal square value. And signal what we are going to receive is S2t minus S1t multiplied with the ASK output. So either it is a square cos square omega ct or it is 0. And that's why here we are considering only that instance when the maximum output of a square cos square omega ct we are going to obtain, and that will exist for only 1 bit period. So the integration time we are taking at 0 to dB. But we have seen that it is 2a square 2 is in the multiplication because we have said that it is dual sideband value. Dual sideband, that means 2 should be in multiplication, because at f plus fc and at f minus fc with the same magnitude, that signal is going to exist. So here this a square cos square omega ct is multiplied with 2, but that 2 is constant, so it is taken outside the integration value. And this eta is going to represent the value of GNF. GNF is nothing but what? Noise power spectral density. So P square T, here gamma square max, you are seeing it is what? Integration from minus infinity to plus infinity, PF square divided by GNF. So here PF square is substituted as integration value of obtained PT signal square, magnitude square. GNF value is nothing but eta. The P square T signal is going to exist only for bit period with the value of a square cos square omega ct. But from in minus infinity to plus infinity times, in between that, only at 2 instances of frequency, this signal magnitude is a square cos square omega ct, and that will appear at the frequency of f plus fc and f minus fc. So this a square cos square omega ct is multiplied with this 2 value. This is how the gamma square max value has been obtained. Once again, you have to solve this for integration of cos square omega ct, and you have to substitute the limit. So here a square was present, here cos square omega ct you have to substitute. There in the denominator 2 will appear, that 2 and this 2 will get cancelled, and you will get the final answer as a square tb divided by eta. Now this is your gamma square max value. This gamma square max you are substituting for this gamma max by 2, and that's how here the Q function here, which was in terms of gamma max by 2, here that will be obtained as a square tb divided by 4n, because it is a gamma max divided by 2. Gamma max, so here square root will appear. Inside the bracket a square tb divided by this eta will be there, but that will be divided by 2 is there, so this 2 will appear as a 4n, because this eta and this 4 we have taken outside to this square root, so it is appearing as 4n. सगळं डिजिटल कम्युनिकेशन बाय श्याम षण्मुगमच्या बुक मध्ये आहे, आणि जो थेरी पार्ट आपण एक्सप्लेन करतोय तो थेरी पार्ट फक्त हा डिजिटल कम्युनिकेशन बाय सिंग सप्रेचं जे बुक आहे, अशा 2 बुकचं कॉम्बिनेशन करून हा चॅप्टरच्या ह्या नोट्स मी तयार केलेल्या आहेत. आणि एक्झाम मध्ये आतापर्यंत, आता माहित नाही तुमची एक्झाम कशी होणार आहे किंवा काय, पण आतापर्यंत हे डेरिव्हेशन्स सुद्धा विचारले जायचे, जे 8 किंवा 12 मार्कापर्यंत आपण तो क्वेश्चन पुटअप करत होतो. सो हियर understanding of the concept along with the mathematical derivations is very important. Then the next type of ASK receiver is non-coherent ASK receiver. आणि नॉन कोहेरंट ASK रिसीव्हरला आपण काय म्हटलं? एनव्हलप डिटेक्टर. एम मध्ये सुद्धा तुम्हाला एनव्हलप डिटेक्टर मेथड होती ना एम्प्लिट्यूड मॉड्युलेशन मध्ये, आठवतंय का काही?
येस मॅम.
Hello. The same envelope detection method we are using in ASK, because ASK is type of AM itself, and this is called as non-coherent ASK because at this receiving end you are not having the locally generated carrier, but the blocks of low pass filter, sampler and the thresholding device, which are the common blocks of receiver, those are going to be present. And that's why here we are saying that again from the channel we are starting. On the channel, the transmitted signal along with the noise is present, which is mentioned as VT signal, that will be given to the first component of receiver, that is band pass filter. After the band pass filter, a combination of rectifier circuit and low pass filter will form the block of envelope detector. After this envelope detector, the sampling is going to be carried. This sampling is also carried after every TB duration, and then the sampled output will be provided to the thresholding device. And every time this sampled output will be compared with some T0 value. If this sampled output is greater than T0, the output for this device will be 1. And if this thresholding device level is less than the sampled output, then the output decoded will be 0. In this way, this demodulation process is going to happen. And that's why we are going to see this in mathematical form representation. So let's start from this VT signal. But VT is what? Actually received signal. And received signal will be addition of your original transmitted signal with the noise component. And this will be present if Bk is equal to 1. Because when Bk is equal to 1, in the ASK modulated output, S2T signal was present. And if S2T is present, that means A cos of omega Ct is present. But when Bk is equal to 0, S1T signal is present in the output, and S1T we have considered as 0, and that's why here Vt will become equal to only NIT signal representation when Bk value is 0. Where now this NIT is nothing but the noise component in the received signal, which is a zero mean Gaussian white noise concentration. Now, either this A cos of omega Ct plus NIT or this NIT component will be applied to the band pass filter. And this band pass filter will have bandwidth of 2 divided by dB. And that will be centered around this Fc. Because we have seen in this presentation that if I have to get the spectrum for the ASK output to be plotted, it is centered around this Fc value. And that's why we are saying this Fc, around this Fc, that is carrier frequency, these ASK spectrum has been centered out. That's what we have mentioned over here. Then we are saying that this signal is going to pass without any much distortion. So after getting the filtration to be done for the band pass filter, we will get the output as AK cos of omega Ct plus Nt, because our signal is A cos of omega Ct plus Nt, or it will be only Nt. Now, when I will see this signal, I can separate out this noise component in terms of the two noise component signals. One will be the cosine component and another one will be the sine component for that signal. So, AK cos of omega Ct will be retained as it is, but this Nt will be elaborated as Nct cos of omega Ct minus Nst sine of omega Ct. But at any instant k, the value of AK, that is amplitude value, will be equal to A if the Bk value is 1, and if Bk value is 0, the amplitude value will be 0. That means either this A cos of omega Ct or 0 will be present for this component of AK cos of omega Ct. And this noise Nt will be the band pass filtered noise output, while Nct and Nst will be said to be the quadrature component of this noise value. Now, if I'm considering this as A and B values for the representation, then in the envelope, I will find out both magnitude and phase will be present. And this will be given as RT cos of omega ct plus theta t, where this RT is obtained as square root of the magnitude squares, that is AK plus this NCT both square plus here this AK plus NCT bracket square plus the another component magnitude is NST, so that's square. So RT is nothing but the magnitude of that signal, and that will be obtained as square root of magnitude squares. The output of the envelope detector is this RT signal, and transmitted bit sequence BK is to be recovered from the kth instance output of this RT signal. And the probability of error is going to lie if I am saying that the transmitted bit is 0, but we are detecting that as 1. That probability is going to lie with the half probability value, and the another probability will be if we are actually transmitted the bit as 1 and we are detecting that as 0. So that another error probability is existing, but this error probability is again with the half value. So this is what the probability of error consideration. Now, in the next part, we are seeing what is the probability of error in estimating zero value incorrectly, and what is the probability of error in estimating the error when the bit value is 1. And we know the periods for existence of either 0 or 1 in the bit sequence are exactly opposite to each other. And that's why if you are observing the limit a by 2, which is starting limit over here, while here for this integration it is the ending limit. But we know that overall error is going to exist from minus infinity to plus infinity. So that limit from minus infinity to plus infinity has been divided with respect to this a by 2 value. And that's why one's limit is starting with a by 2, while another limit is ending at a by 2. Then this r by n0, r is nothing but the value of that noise that we have obtained in the previous case, divided by n0. N0 is noise power spectral density, e raised to minus r square divided by twice n0. So here we are putting the values of a by 2, which is the magnitude obtained for each of the bit period value, which is common for both the sides. So here a by 2 and here also a by 2 is existing. And here Gaussian probability density equation for the probability we are going to observe. So it will be 1 upon under root 2 pi n0, which is the noise power spectral density for the noise, e raised to minus r minus a bracket square divided by twice n0. Here r minus a is done because when the amplitude of the signal is a cos of omega ct, there r minus a we have to do. Here for this case the amplitude of the signal is 0, so that is equal to r square itself. So both equations are one and the same, but in this case here we are not having any of the amplitude of the signal, so variance value in terms of 1 upon under root 2 pi n0 was not existing for this case. Instead of that, r by n0, which is a constant term, that is going to present for this probability of error to be obtained. So this is how we have obtained the value of probability of error for this 1 bit value as 4n0 divided by 2 pi a square e raised to minus a square 8n0. And that probability of error will be having always the magnitude square is greater than the noise power spectral density. And the last comment what we are saying is always the probability of error for the ASK modulation, which is coherent one, is have less amount of probability of error with respect to non-coherent ASK modulation. But the design of non-coherent ASK modulation is very easy and simple, because you have seen in the coherent demodulation we were having the blocks of integrator, we were high gain amplifiers, then we were having two switches which were existing, while in case of non-coherent amplifier only the envelope detector was the block which was existing in the receiver portion, and that's why its design was very easy as compared to coherent ASK demodulation. And within next 2 minutes I will give you the attendance poll.